start at 10.4, and we talked about the fact that there's kind of two different components to 10.4. One component is talking about measures of central tendency, and that's the component we did last time. And we learned 3 central tendency measures. What were they? Mean, median, and mode. Okay, good. And they're good for different things. Kind of talk a little bit about that as well. If you've started some of the homework, that's great. You certainly didn't need to or whatever, but they're going to have some different cases where you're going to have to think about what makes the most sense to talk about in this particular situation, the mean, the median, and the mode. Now, the other thing in this section is variation. Now, variation is how far something is off from that central tendency. How far are we away from the mean or the median or the mode, that kind of thing. So we're going to jump back in with range, interquartile range, and then a lower and upper quartile. So range is kind of like the domain and range that you remember from algebra. Okay? So when we talk about range in algebra, we talk about what y values are allowed. Do you remember that? Well, okay, if you don't, it's okay. And then the domain is x values. Well, the range is, again, the kind of values we're allowed, or in this case, the kind of values we actually have. So when we talk about the range, what we do is we take the largest value and we subtract the smallest value. So raise your hand if you can do that. You should see 20 hands all in the air. Well, 19 because Brady's not here. You guys can subtract. This is an easy calculation. All it does is it tells you how spread apart the data is. Okay? So if you wanted to know heights of people in your family, you take the tallest person's height and the shortest person's height and you subtract. That's all range is, just a subtraction. Okay? Interquartile range is another subtraction. It's a subtraction of something else. It's a subtraction of the first or the lower quartile and the third or the upper quartile. So let me talk about what those quartiles are. All right, so the lower quartile is the value below which 25% or 1/4 of the scores lie. And the upper quartile is the value that's 25% above. So imagine if you actually put all of, like in our class, it would actually work out really nice to 20 people. So imagine I put your tests in order, or your grades in order, whatever, from least to greatest. Okay? So I could actually physically split the stack of papers or physically split the grades. And the lowest 25% would be the lowest 5 scores would be the lower quartile. Those would be in the lower quartile. The top 5 scores would be my upper quartile. Can you picture it happening? Well, whatever that maximum score is that splits off the lower scores, and whatever that minimum score is that splits off those upper scores, those are the inner and the outer quartile, or the upper and the lower quartile. Okay, we're going to find once you can see it actually in the picture. But those two numbers then, whatever they are, if you were to subtract those two numbers, that's the interquartile range. Okay? So what it does is actually tells you the middle 50% of the values lie between this and this. They're spread apart by maybe 20 points or something like that. Okay, that's what that tells you. So let's take a look. I think I have one more slide of information. Okay, related to interquartile and interquartile and outer quartile is the idea of a box plot. You may or may not have seen this before. If you haven't, it's fine. But sometimes it's also called a box and whisker plot. Let's see why in a minute. And if you have the TI 83, 84 calculators, here's one right here, they actually will do box plots for you. I have not played around with them very much, but I know that they're in there because I've seen them on more than one occasion. So this is something that is used because it's got a really good visual for this kind of information. So the box plot, as well as needing the interquartile and the outer quartile, both of those, it needs the median. That's the 50% mark. We talked about median last time. And it also needs the upper extreme and lower extreme. That's just your top value and your lowest value. In fact, your book doesn't do this, but I will tell you that sometimes when I do my grade distribution, especially in classes that I have people that have very disparaging grades, that they're really far apart. Sometimes when people do means, for instance, they'll throw out the lowest so many and the highest so many because they're kind of throwing out the extreme values and they're trying to focus on the majority of people that is average. I tend to do that when I know I have people in my class that aren't coming to class. I don't really care what they fail. I mean, I care if they're failing or misunderstand, but it's not my fault. I mean, if they're not coming to class, I can't control that. I don't have any way to affect that change. And so sometimes I'll throw those values out because it doesn't really reflect on me, and I'm trying to figure out a reflection on me, how my class is doing. So these lowest values and these highest values, to give you some perspective, I had 2 9s. 9 out of 100 on the last test. 2 9 out of 100. 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 2 9 out of So, yeah, something about that just doesn't sound like it's false. I don't know. Maybe it's just my imagination. Maybe wishful thinking. But these lower values, these upper values, the actual upper extreme is the absolute largest, and the absolute lowest is the lowest lower extreme. Okay? All right, so we're going to create a box plot. So there's several pieces of information we need for a box plot. We need the median. We need Q, and also the median is sometimes also called Q2, just so you know. We need the lower quartile, which is Q1. We need the upper quartile, which is Q3. We need the lower extreme, that is the lowest value, and we need the upper extreme, the largest value. So we need all of these values in order to construct this plot. So we'll start by just finding a bunch of different values. And so what would be helpful to do with this list of values that I have? Put them in order, right? Smallest to largest. So that's what we're going to do first. And you should recognize this list of numbers. We've already worked with it once before. Last time, actually. So putting them in order, what do I have? 12?
17, 18, 22.
30. We found the median for this last time. What was it?
18.
18. Now, visually, this is my median then, right? Because it splits the data in half. Half the data is to the left, half the data is to the right. Can you picture that? Okay, so my median was 18. Now, if you cover up from this median over to the right, we have three numbers, 12, 17, 18. To find Q1, that is the inner quartile, we find the middle value of those three, which is 17. So this is Q1. And we do the same thing for the upper quartile. I cover up my median to the left. I have 22, 22, 30. What is my upper quartile? So Q3 is 22. And then the lower extreme is 12. And an upper extreme, 30. Okay, so finding those values is just like finding medians. Finding Q1 and Q3 is exactly like finding medians. It's just finding the median for half of the data set at a time. All right, so let's talk about what a box plot looks like then. Okay, so in order for a box plot to make sense, you've got to have a number line somewhere on your diagram. So we're going to see if I can find my number line. We didn't do such a good job last time finding things, but we did find them, didn't we? Cards. Okay, I could use a ruler, that would be okay. I think there's a number line in here somewhere. Oh goodness. Measuring spoons. This is just an opportunity for you guys to see all the cool stuff that is inside here, right? That's what I was doing this for. Make our own. Okay. I believe it's there, but I'm not finding it, so we're just going to make our own. All right, so we're going to draw a number line. still downhill. Maybe I should try that one more time. It's okay now. And in fact, I'll move it down. All right. I need to have on this number line equally spaced increments, of course, and they need to have all the numbers included that I have included here. And they need to be equally spaced. Okay? So you can't just put a 12 and a 17 and an 8. I mean, you can't just put these 5 numbers on there and sort of make them look like they're all equally spaced, because of course they're not. There's more space between the 12 and the 17 right here, for instance, than there's going to be between the 17 and the 18. I know that sort of sounds like you know that, but I'm saying it because it has happened that students don't recognize they're doing it. So if we're taking a look down here, I'll start with 12, and we're going to equally space them across until I get to 30. When it doesn't work, you go backwards and make it work. All right, so here's 12, 13, 14, 15. They do not all have to be labeled, but having a few of them labeled to give yourself some perspective would be a good idea. All right, so here's what you do. You're going to take your pencil, and I'm going to take a rectangle. And I want a rectangle that has one of its vertical sides at the lower quartile and one at the upper quartile. So I'm going to have a rectangle that extends from 17 to 22. Okay? So 17 for me is about right here, and it's above the line, okay? The line is just giving us some perspective is all it is. Okay, so this is Q1 over here, always, and this is always Q3 over here. Good so far? And then we're going to put a vertical line in the middle of this thing, not the literal middle, but the median middle. Okay, so wherever the median was in your particular data set, and this one's at 18, and my 18, oh, I started at 16. Nobody wanted to tell me I messed it up? Yeah, I know. What's up? Nobody's going to talk to me. Just let me mess it up again, huh? All right, let's fix it. We're going to start it here. Q1's right there. We're going to make a vertical line down at 18, the median. Something like that. That's the box of the box plot. And you're about to see now why it's called a box and whisker plot sometimes, is that you take the middle of the box, that is the horizontal or the vertical middle, and you're going to draw your line from this middle out to the lower and the upper extremes. Those are sometimes called whiskers. Magic cat. Yeah. So that vertical line at 18 is not so vertical, but. All right, so this tells you a lot of things, actually, when you look at it. It tells you that the upper extreme, which is now over there, yeah, it's okay, my 30 is just written a little bit to the left of where 30 is. It tells you that the upper extreme is further away than the lower extreme, and you can just see it. I mean, you don't have to think how far away. I mean, you can just see the upper extreme is much further away from the median than the lower extreme, right? You can see that the middle, which was 18, 25% of your data values lie between 17 and 18. I know this isn't a big data set, but you can see that from a picture. You can see from 18 out to 22, you've got 25% of the data here, right? You can see that 25% of the data goes from 12 to 17 right here. And 25% of the data goes from here over all this way to 30. Okay, you can see a lot of information just real quick. It's kind of like when I do my stem and leaf plot when I'm looking at grade distributions. I can see really quickly I've got a nice curve that does like this or whatever. Okay, so that's what this is doing for you, is it's giving you that picture form of how things are spread apart. You good with this? I think this is the only graph picture kind of thing you're going to work with in this section. The other thing you're going to work with is two different kinds of deviations, okay? The first one is called the mean absolute deviation, as in MAD, M-A-D. It makes use of absolute values to find distances from the points away from the mean. So this one's actually considering the mean. The last one, the box plot, was the median, right? Everybody good with that? This is the mean. It's found by taking all the absolute value differences and averaging them together. Okay, we're going to do one in a minute, but it's a really straightforward calculation. Okay, that's the mean absolute deviation. The other one is a little bit more difficult. The standard deviation has more steps to it. So you see a 6-step process that I've written out. Okay, so here's the deal. The standard deviation is actually the square root of something called variance. And this piece right here, 1 through 5, if you only do 1 through 5, you actually find the variance. Step 6, taking the square root, that's how you get the standard deviation. Okay, so this part in red finds the variance. And then you take the square root at the end. So we're going to do, and it's the same data set that we've been working with. So if we had not already done so, we would actually have to find the mean, because as you notice, both of these methods talk about the mean. Do you see that? Mean absolute deviation has the word mean in the title, and the step 1 of the standard deviation process is find the mean. So you have to find the mean, have to know the mean to do these. We actually found the mean for this last time. So flip back to example 1 or 2 or whatever, and this was in the set of numbers here. What did we find as the mean? Okay, and just so that you know a standard notation for it, the mean is often written as an X with a bar on top of it. Standard notation for mean. And 19.9 is what we found it was. And just so that you remember that you did this before, this was from example 1. Yes? All right. So we already found the mean. All right, so directions say, find the mean absolute deviation, the variation, I should say variance, typo, the variance, and the standard deviation. All right, so we're going to do mean absolute deviation first. Everybody ready? Both of these are going to be easiest to find if you put them in a table. So here's what I mean. We're going to create what's going to look kind of like our grouped frequency. Remember we did those frequency diagrams from section 2? We're going to actually just list all of the values out along the left-hand side. And if they repeat, we're going to list them twice. Okay, so you can either put them in order smallest to largest, or you can just put them in the order they were given to you, which is what I'm going to do. So 18, 22, 22, 17, 30, 18, and 12. And these values are the X values. The data values are called X. And what we're going to do next is we're going to take each of those X values and subtract them from the mean. What I really want to know is how far away are they? Because there's absolute values, what does that tell me? It's always positive. So I don't really care whether it's smaller than the mean or bigger than the mean. I just want to know how far apart it is from the mean. So you can literally take your calculator, and on each one of these, you can take them, 18 minus, and do minus 19.9. And no matter what it says, positive or negative, you're going to write the positive part down. Okay? So, Chelsea, I'm going to let you tell me them because I see you've got a calculator going on back there. So let's just go in order. I want you to do this, okay? Do 18 minus 19.9 and tell me what you get.
1.9.
Okay, and then 22 minus 19.9.
2.1.
Okay, so she's giving me only positives because we really want the absolute value here. I've got another 22, so I've got another 2.1. What's 17 minus 19.9?
2.9.
30 minus 19.9.
10.1.
18 I already did, so we're good there. And then 12 minus 19.9.
7.9.
Okay. Does everybody know where those numbers came from? Because now it's time to ask if you're not so sure. Okay, so what we do is we add those all together and we divide by how many we have. In other words, we find the mean of those absolute values. That is the mean absolute deviation. It's the name, right? Mad. No, very creative name right there, but it works. So You're going to add 1.9 plus 2.1, 2.1, 2.9, 10.1, 1.9, and 7.9 all together. Somebody tell me what the sum is before you divide. 28.9. What should we be dividing by? This is my sum. And then we divide by 7. This will give me my average. So I shouldn't say sum here. Say we're actually finding the mean absolute deviation. So what do I get when I divide 28.9 by 7? 4.13. 1 or 2 decimals is sufficient. We have either one. Any question on this process? This is the easier of the two. All you do is subtract all these values, subtracted them, right? And then you add them up, divide by 7. All right, so the standard deviation and the variance, this component is a little bit more, it's just more work, okay? So, I'll change colors. Our table is going to start out looking very similar. I'm going to start with an X, then I'm going to write them all down. And again, you can put them in order if you want. They certainly don't have to have any particular order. And I'm going to actually do this in a couple of steps because I want to make sure that everybody's clear on the steps that you've got. And the steps are actually coming back from this last slide. We've already found the mean, number 1. Okay? Number 2 says subtract the mean from each number. So in this column right here, I'm going to do the mean subtracted from each number. So we're going to do exactly what we just did on the last one, except that we're going to keep the positives or negatives. Okay, now they're going to go away in a little bit, but for this column to actually be accurate, there will be positives and negatives in this column. All right? So in each one of these, you're going to take the value minus 19.9. So what is 18 minus 19.9? Negative 1.9. How about 22 minus 19.9? That one's positive 2.1, and we have a couple of them. Now we're going to have 17 minus 19.9. 30 minus 19.9. 18 minus 19.9. We already did that. And then 12 minus 19.9. Oh, 9, sorry, thank you. We're wrong. All right, so we're not adding these up, though. That's not the next step. What does step 3 stand supposed to do? Square them. All right, so let's remind ourselves what we've got here. This was step 1. This is step 2. I'm about to do step 3. And what step 3 does is it takes the values from the column before, and with the help of your calculator, if you have it, it squares them. And so what happens when you square a negative? It becomes positive. The C doesn't become positive until now, okay? So as you're entering these in your calculator, do you really need to type in negative 1.9 and then square it? No. If you just type in 1.9 and square it, it will do the same thing. Is that okay? All right, so these are all going to turn into 2 decimal numbers now. So what is 1.9 squared? 3 point what? 3.6?
I got a 1 after.
Okay. 2 decimals. They're all going to have 2 decimals, so we'll keep them accurate as far as we can. At the very end, we can round to 1 or 2 decimals, but don't do any rounding in the middle. Question, Kayla?
Should that have squared?
Oh, I've left it off, yes. It should, thank you. Yeah, we want to square. Okay, what is 2.1 squared? 4 point what? 4.1? And I got a couple of those in a row here. How about 2.9 squared? 10.1 squared. Good. I already did the 1.9, so that's another 3.61. And then how about 7.9 squared?
62.42.
I think it's 4.1. I think you're going to get a 1 at the end, yeah. All right. What's step 4? Find the sum. So now I'm going to do basically what happened on the last problem, the mean mean absolute deviation. I'm going to add these together now. So I'm on step 4 down here. And add those up. So what is 3.61, 4.41, and so forth down? Do I have a second? Yeah? Awesome. Okay, so that was step 4, easy enough. We added things together. And then what are we going to do on number 5? Right. So on step 5, I'm going to take this value that I have, 188.87, what will I divide by? 7. And if I do, what do I get? Now, let me tell you that this is the variance. Variance does have a symbol as well. Mean was the X with the bar. Mean absolute deviation, we abbreviate MAD. When we do the variance, I know it sounds like maybe we should do V, but V is used for some other things in math, so we don't. We actually use S squared. Sometimes if people are using Greek letters, which there's a reason for doing that in different cases, they'll use a sigma as the Greek letter squared. Again, I'm not getting too far into statistics, but you will see that used under certain circumstances. This is the variance. So what do I do for standard deviation then? Square root it. And what do you think happens when I take the square root of S squared? What do I call it? I call it S. And that is actually exactly what the standard deviation is called. And now you see why we're using an S. So I will take the square root of the 26.98. And at the end here, if you can give me at least one S decimal, at most 2. So either a 1 or a 2 decimal answer, that's what we'll round. What is the square root of 26.98? 5.19. So that's my standard deviation. This is my variance. And this is my mean absolute deviation. And they're all telling you how spread apart the data is, but in a different way. Okay, there's one more item in this section to talk about. Do you have a question, Chelsea? Or Charity?
There's only 6 steps, right?
Yes. I think, yeah, 6. Yep.
Why did you have to find
There was 2 things we were asked, well actually 3 things we were asked to find. The mean absolute deviation, which was the 4.13. The variance, which we found at the step 26.98. And then the standard deviation, which is the 5.19. So it just depends on what the problem's asking. And I just did all one problem, so you can see all the steps. But if it asks you to find a standard deviation, you don't need to find the mean absolute deviation to do that. And I will say, I've asked a question on a test before where I asked for one, and students give me both pieces of information. I want to know if you know which one's which. So don't give me more parts of things than I've asked for either, because that just tells me you don't know what the difference is. Just give the piece of information you're asked for on a particular problem. All right, last piece of information in this section. Distributions. All right, so we're going to talk about a normal distribution. You've probably heard the phrase before, bell curve, right? Or perhaps you've tried to tell a teacher that you want them to grade on a curve. Little did you know that the curve you think you want them to grade on is probably not the curve that you actually said you wanted. When students say they want you to curve, what does it mean you want them to do? I want you to increase your grade. That's what you want, right? That's what you mean when you ask for it. When you're actually grading on a curve, what it means is it means that you have an image that looks like this. In other words, if I were to look at a bar chart, or if I were to look at a distribution, and Jupyter will do this for me. If I were to look at a distribution of grades, I would expect it to have this sort of a curve to it. And, you know, in really, really large lecture sections, that sort of makes sense. You can kind of see that that would be reasonable. The majority of the people are right here in the middle with Z's, right? You've got kind of a few B's on the edges, and the D's kind of out, you know, balance out the, you know, on the 2 edges. And then you have this nice, you know, very, very small number of A's and a very small number of F's. That's what that means for something to be a normally distributed, normally distributed, we usually say function, but let's say situation. All right, so here's what a normal distribution looks like, but it really, truly is a normal distribution, okay? So when you have a normal distribution, this value right here is the mean. So the value dead center at the peak of the bell, okay, the very top, that's actually your mean value. So if we were to say, oh, the average on the test was an 82, that 82 would be the middle value, okay? And then one standard deviation in each direction, this is why we talked about standard deviations and how to find them, means that we move out one standard deviation and 68% of the data should be between the value one higher and one lower than where you were. So this is one standard deviation out. In fact, let me do it this way. You would have 68% of your data values within one standard deviation of the mean if the distribution is normal. If you go out, so this is one standard deviation in either direction. If you go out two standard deviations in either direction, I know I'm not putting positive or negative, I'm just talking about distance here, so that's why you're seeing that, okay? If you go out far enough that you're just spread out two standard deviations, how much value is between there, does it say? 95%. So from here to here. So all of this area, including the part that we just trapped in the middle, okay, including that piece, that is 95% of the data. And then if you go out to 3 standard deviations in either direction, that is almost the entire thing, isn't it? And all that shaded part in there in green, virtually everything, exactly how much is it? 99.8% in green. Okay, so nearly all of the heights of people fall within 3 standard deviations of the mean. Nearly all weights of football players fall within 3 standard deviations of the mean weight. Okay, something is normally distributed, then that's what's going on. And if you've ever noticed, you probably have not ever seen this or thought about it this way before, but this is what happens when people do packaging for your food products in the store. So imagine your box of cereal. It says 12 ounces on the box of cereal. If you were to physically go and you were to weigh that box, it may not weigh exactly 12 ounces. Okay? But it's normally distributed within just a little bit of the error, right? And there has to be an acceptable amount of error for them to be okay with labeling it 12 ounces. Because if they put 12 ounces on there and almost all the boxes are 10 ounces, we're going to have a problem, right? People are going to start figuring it out and they're going to be like, hey, what happened here? And they're going to get some false advertising problems. Okay, so normal distributions are used in a lot of different things. I want to show you how we can think about them with some examples. All right, so we're going to assume a normal distribution that an average phone call in a certain town lasts 4 minutes with a standard deviation of 2 minutes. It says what percent of the calls lasted less than 2 minutes. So anytime you're working on these with normal distributions, you're going to draw that picture that we just had on the previous slide. You're not going to draw it with all the colors and all the things in there quite like I just did. You're going to do it with whatever information you're given for this problem. So you're first going to start by drawing developer, okay? And it doesn't need to be perfect, just draw it. What do you think you might put into this picture? Average, right? It said the average length of the phone call was 4 minutes. So this right here is 4 minutes. And you know you can go 3 standard deviations in each direction, correct? I mean, we could write these out 1, 2, and 3, and 1, 2, and 3. But how far is the standard deviation in this particular problem? 2 minutes. So I am going to label the one that's to the left of this 4 with the number 2. It's 1 standard deviation, but 1 standard deviation here is 2 minutes. So 2 minutes on the left, and we would have 6 minutes on the right. And I mean, I could fill in more of the details and it'd be okay, but I don't need any more of the details. Because what am I asked to find? What percent lasted less than 2 minutes? So on my picture, here's my 2 minute mark. Which part of my picture am I concerned with? The left. So I'm going to shade it in. What I want to find is I want to find the area that I just shaded. And there's at least a couple ways to do that. Based on those 68, 95, and 99.8 numbers that we had on the previous slide. What could you do? I know why you're using 95, but don't do 95. Can I do 100? Okay. All right, so underneath this curve is 100% of the data. Everybody okay with that? 100% underneath there. So if I were to take 100%, Whitney told me she'd like to subtract 68. Why would that help? It'll take out the middle. So here's my 68 in my middle right now. So if I do this and I take 100, the whole thing, minus the 68 in the middle, does that give me the piece I want? No, but I'm close. Then I would need to divide by 2. Because what that would actually give me before I divide by 2 is both of these tails. The tail that's less than 2 and the tail that's more than 6. But I only have one of them. And this is a symmetric curve. So I can do these sorts of things where I can subtract and I can divide and whatnot. So 100 minus 68 is what?
32.
And 32 divided by 2 is? So this is 16%. Did anybody else, can everybody think of another way to do the problem? There is one more way to do it. Kaylee. So let me take a step back. Why are you using 50%? Okay, so you're going from the 4 over to the left, right? That's half of my picture, 50%. Everybody with me? So what would I do with that 50% then? Minus half of 68. Because half of this 68 is going to be right here, and the other half is going to be right here. So half of 68 looks an awful lot like what number? 34. So this could be 50 minus 34 to give me 16%. Those are the two most common ways of thinking about it. Of course, you see they give you the same answer, right? Doesn't matter which one you use. But they definitely are thinking about it differently, aren't they? I mean, the picture that you're having in your mind about what you're doing, it is different. Okay, let's take a look. So the answer is 16%. Let's take a look at the next one. IQ scores are normally distributed. It actually is one of those things. And the reason is, I mean, we have created tests that force that in some sense, right? You know, that there's just sort of an arbitrariness to them, but to the way that they're created, that is. The mean IQ for 1,500 students is 100, with a standard deviation of 15. Assuming the scores have a normal curve, we're going to find some pieces of information. So the first thing you're going to do is draw a picture. So we're going to draw in this picture. And what am I going to label in there first? The mean. And what is the mean? 100. What is my standard deviation? 15. So if I go out one standard deviation in either direction, what's my lower one? 85. And my upper one? 115. Because I know where I'm headed with this problem, I'm going to keep going and label all of them because they're all going to be used at some point. What if I go one more standard deviation out? Where am I? 70 and 130. Okay, let's do one more. 55 and 145. So this is my picture with all of them filled in. First question I want to ask you is look at the way the question is worded compared to the last slide. What's different? It says how many, it does not say what percent. And I still have to find the percent, but I will not be finished when I find the percent. Okay? So we'll counter that in a second, but I want you to be aware of that. Be sure you're answering the question that's asked. Don't stop too soon. First question says, how many have an IQ between 85 and 115? 68% is the right answer for a percent. So how do I find 68% and find the number of people?
68 over X equals 68 over 100. Oh, I guess you have to do it.
Okay.
That's how I do it.
All right, so you can do 68 over 100 equals
X over 15.
X over 1,500. You guys are good at proportions since we worked with them. So you can do this. What else did you do?
Jack and Jill plus one.
Jack and Jill.
You did, I always think of like 68 over X, is that right? 'Cause I
No,
remember
that's
I
fine.
did that on the
Yeah, you can do it that way. Okay, so let's cross multiply. What do you get? How many students would this be? Or how many people would? Oh, yes, it is students here actually too. Yeah. How many students would this give you? 1,020 students. How about between 70 and 130?
same thing.
Yeah, same thing, but with 95%. So 95 over 100 equals X over 1,500. For 1,425 students. How about an IQ over 145? So there's two ways to do it, right? Megan, what do you have? Is it 98.8? 99.8? Okay, do you guys remember that? So we did the last slide, we did it with a different value. So the issue is that if I find this piece, this is 99.8 in the middle, so subtract 100% minus the 99 in the middle, that gives me the two tail ends, but I only want the upper tail, so divide by 2. This is going to give me a percent. What is this? 0.1%, then what? 0.1 over 100 equals X over 1,500, and then what do you get? 1.5. So what should we do? You need to round, because you can't tell me 1.5 students. You can't chop the kid in half. It's not going to work.
So I guess
Probably won't place very well on the IQ test if you chop them in half. Yeah, we're just going to use normal rounding rules. So 1.5 is going to become 2. So this is, and if you want to put an approximately to recognize that you did round that, I'm good with that. This is approximately 2 students, but you must round. I have memories from my first teaching experience, and there was the answer to termite, people using the decimal points of the termite. I know we want to kill the termites, but if you have decimal points of them, you don't have them anymore, they're dead. All right, one last question in this section. Percentiles. This shows a person's score relative to other scores. For example, if a score is in the 90th percentile, it means that approximately 90% of people are below that value. So this isn't like finding your grade percent. That's not what this is, okay? So this would be like imagining, and there are places where you do percentiles. Does anybody know some of them?
like babies or like the first.
Heights and weights of babies, they do it for sure. Went to all my kids' appointments, was always curious about what's going to happen on the height and weight chart. And my kids' head circumference, Eli had a big head. So they did his head circumference in his height and weight charts, percentiles for those. So you have parents being really funny and saying things like, my kid's in the 90th percentile in height, and everybody's like, who cares? Okay. There's another thing that you see percentiles in that are very applicable to you.
SATs.
Standardized test scores. SAT, ACT, end of instruction exams, and you guys are going to be involved in all of them. My daughter's doing all those kinds of testing next week at the elementary school, not the SAT. But, right, like they have the standardized tests, right? All these different things that assess whether the schools are doing their job, whether the kids are learning what they're supposed to be learning. And they give you the answers, or they give you your scores back in percentiles. So they compare my third grader to all the other third graders who took the test in the state or in the school district or whatever, and they can say she's in the 90th percentile. That would mean that she scored at or above where 90% of the students scored. Does that make sense? So it is not a comparison. It doesn't tell you really how well you did on the test. It tells you how well you did on the test compared to everybody else. That's a very different comparison. You guys get that, right? Okay. So This is an example that talks about that. Junior is ranked 50th in his graduating class of 325. Liz is in the 50th percentile, which means something different. Which student then would have had the higher GPA with that information? There's lots of ways to think about answering that. So what are your thoughts?
That's high.
Okay, so Kayla wants to tell me junior, but tell me why you think so, Kayla.
Because 50th percentile would be like half, you score, or your GPA is going to be like half of 10, which would be a greater number, so you could be like, I guess like 100 and something in the class and still be above.
Okay, so junior is 50th highest in his class. What's Liz? If I compare her the same way. I know it's not going to be exact, but approximately. 162. So Liz is 162 highest in the class. Does that make sense? So you're sort of changing that so that you can actually compare them in the same way. If Liz is at the 50th percentile, it means that 50% of the people, so if we take 50% of, how many was it? 325, or divide 325 in half, we get about 162, right? 163, whatever you decide to round, I don't care. But it's far cry away from junior, right? Junior's much higher up in the GPA. So junior's GPA is higher. What else could you do instead of comparing it the way that we just did here? Sure, we can figure out what percentile he's in. If he's the 50th highest, how many people are below him? 275. What could you do to figure this out? No? 275 people out of 325 that are beneath him.
What do you think, 275?
Yes. 84% of the
84 to
folks.
56.
Okay, 84, almost 85%. Almost 85% of the class is a lower GPA than junior, but only 50% of the class has a lower GPA than Liz. So you could convert them into percentiles to think about that as well. Okay, does that make sense? All right.